The question is, can I have some candy? I'm just hungry, that's all. Is that alright? You're willing to handle?
Yeah, I guess so, but you should have some sort of a question.
I just need dinner is what I need. How long do you think I can survive on these without eating real food? There's a question.
Okay. So, let me review spinors, and I'm going to do it from, I'm going to do it by using that trick that I mentioned earlier, which I think makes things simpler. On the other hand, with spinors, I often start out thinking, here's a way to make spinors really simple. And then after chugging a little bit, they still get complicated. So, this isn't going to be perfectly simple. Anyway, if we use the Schwarz's metric and we imagine that we have 4 fields that satisfy the Klein-Gordon equation, then, as we saw earlier, the field psi A of x equal to I d mu gamma mu plus m a b phi b of x will satisfy the Dirac equation. That is to say, I d mu gamma mu minus m psi is 0. Okay. And we want to expand a spin 1/2 field in the usual way. 2 pi cubed over, dqp over 2 pi cubed. And then we have to sum over the 2 spins, or plus to minus, whichever way you want. And then we have u of p and s, some a of p and s, e to the minus I px, plus b of p and s, d dagger p and s, e to the I px. So that's the usual way to expand these things. And so the question is, what are the u's? And we see that any u that is of the form I d mu gamma mu plus m times some u0 e to the minus I px will be a solution of Dirac's equation. And this, of course, is p mu gamma mu plus m, was the u. u0 e to the minus I px. Here, u0 is just some 4 spinor. Let us say momentum 0. No, it's a 4 momentum, 4 0. It's a 4 spinor associated with momentum p. And we want this to be 0, and so, this will satisfy the equation because it's of this form. And u0 can be, in fact, basically any old 4-component object. If we go to p equals 0, then what we see is that u of 0 and s should be, well, this is just m. The other p is 0. So this is m gamma 0 plus m, acting on some u0 of s. And I'm just concentrating now on the spinor part and not on the time dependence. So it looks like that. And now this matrix is just the matrix M times 1, 1, 1, 1. times some then u0 of s. Any questions? Let's see, I once again have violated the de Blasio rule. 100 equations and no statement of where we're going. Okay, where will we be going? We will derive expressions for Dirac's, spinors, and also some of their properties. There. To some extent, satisfied the velocity. Okay, now let's set u0 of s equal to some c and some zeta. In other words, it's a 4-spinor, and I'm calling one c, the other zeta. And so this u0 of s then is m1111 c zeta, and so you see this is just m c plus zeta c plus zeta. Or equivalently, the zero momentum spinor is of the form m something, some alpha of s and some other alpha of s, but it has to have that form. It's some 2-spinor, another 2-spinor. And the point is the upper 2-spinor has to be the same as the lower 2-spinor. And so the natural thing is to say alpha of plus is 1, 0, and alpha of minus is 0, 1. And with that choice, then we have formulas for u of 0, plus and minus. And I'm going to start out using a simpler normalization than the one Schwartz uses. I'm just going to do this, which actually is what is very similar to what Weinberg does. Okay, so we square here. The point is that this guy has to be the same as that guy, and this guy has to be the same as that guy. And they have to be obviously orthogonal because they're different spins. And I don't know, state law says Z is up, and yes.
I'm confused as to, we're talking about spin 1/2 particles.
Yeah.
Yet we choose to represent them as these 4x1
Yes.
matrices.
Yes, those are the spinors, yes.
But we could just equivalently represent them as a 2x1.
Well, that's what I did about maybe a week or two ago.
Okay. Gotcha.
And then we had, that's for the left-handed and the right-handed.
Okay.
But the deal basically is that let's see, there are two things going on here. One is that the mass term, well, first of all, the mass term mixes the left with the right. Okay? So you, unless you're talking about massless particles, you've got to have both left and right in the theory. And Dirac showed us how to put them together in a nice way. That's why it's 4 components. And that, of course, is a very good question. There's no, what is it, no fructose.
I know, but
Okay.
Halloween just happened, so.
All right.
A whole lot.
Okay, I admire your restraint. All right, so, but that's of course an important question. I don't know why we have to have so many goddamn wires. It reminds me of, you know, we've got Wi-Fi and what's it, Bluetooth?
Yes.
Bluetooth.
So we should be able to dispense with these wires. And then, of course, we also have computers. And so we were supposed to have the paperless office. Instead, we've got a Xerox machine the size of a small car. And it chugs away and eats up half the department's budget. So paperless.
You say that as you hold your printed lecture. So you're actually part of the problem.
Yeah, I'm as guilty as the rest, yes. Okay, so these are our two basic spinors adopting a simple normalization, and now we want to use this formula here that U of P of S will be, this is the P dependence, and this can be just any old thing. And the any old thing we're going to be talking about are these two guys, apart from possible overall normalization. So that tells us then that we want U of P plus to be 1 over 2m. All right, so let's see. I'm skipping perhaps a step here. What is this P mu gamma mu? Well, P mu gamma mu, this is E gamma 0 minus P dot sigma, P dot gamma. So that's what P mu gamma mu is. And now gamma 0 then means we have an E here and an E there, because gamma 0 is 0, 1, 1, 0, written in, this is a 4 by 4, so this is a 2 by 2, 0, a 2 by 2 identity. The gammas themselves are 0, sigma, minus sigma, 0, where these are the Pauli matrices. And so consequently, what we've got is E minus P dot sigma, E plus P dot sigma, 0, 0. But then we add M. So what we have then is, and we can rewrite, let me rewrite P mu sigma mu, P mu gamma mu. P mu gamma mu, it can also be written as 0, P sigma bar 0. That's the way I'm going to think about it. This is then thought of as P as a 4 vector, sigma as a 4 vector, first component, the 2 by 2 identity matrix. And since it's Lorentz, we have a minus sign. The bar here means that we flip the sign on the sigmas, so we have a plus sign here, because it's Lorentz and flipped. Okay, and then we add M. So we have P mu gamma mu plus M, so that's M P sigma bar. And then this thing is what? Well, it's going to be alpha plus, where of course alpha plus is just 1, 0. Well, over there, alpha plus is 1, 0. Okay, so altogether then, this is 1 over 2m, m p sigma minus, well, plus p sigma bar, m on 1, 0, 1, 0. And so this is 1 over, I think this should be a 2m. 1 over 2m, m e minus p dot sigma, e plus p dot sigma, m on 1, 0, 1, 0. And now if you multiply this, for some purposes it's good to just stop here, because this is a nice simple expression. But if you want to see explicitly what the four spinors look like, well then you just multiply that out. And you have 1 over 2m. So this is m00m, e minus p3 minus p1 plus I p2 minus p1 minus I p2 e plus p3 e plus p3 p1 plus I p2. Well, this isn't lining up very well. There. P1 minus I, P2. I'll send you guys this tonight or tomorrow. P1 minus I, P2, E minus P3, M00, M. All that times this thing, so. All right. When you multiply that out, what you get is U of P plus is 1 over 2m. M plus E minus P3 minus P1 minus I P2 M plus E plus P3 P1 minus I plus I P2. All right, so puzzle there. This is okay. Yeah, what puzzles me a little bit here is this. If we go to the p equals 0 limit, this is 2m. That cancels. This is 0. This is 0. Yeah, this is 2m also. Okay, I guess it's all right. What puzzles me, though, is that if this is moving in the z direction, this term is bigger than that one. That seems just a bit odd. So,
what would you expect it to be?
I'd expect that this would be the same or bigger than that. Just a naive expectation. If somebody has a good fast internet connection, wants to jump on the web and look at Wikipedia and see, maybe not. All right. What is U of P minus? Spin down. Well, this is 1 over 2m. M P sigma bar, M, and now it's alpha minus, and so that is 1 over 2m, M P sigma bar, M, and now 0, 1, 0, 1. And now, if we multiply this out, and if I haven't made any mistakes, I'll skip some of this. What I got was minus P1 plus I P2, M plus E plus P3, P1 minus I P2, E minus P3 plus M. And I must say this one looks better than that one because this is the spin down and this guy is bigger. On the other hand, if you do 1, 0 into this, that's what you get. So I don't. For the antiparticles, what we have is we're going to say it's I d mu gamma mu plus m some v0 e to the ipx, and it's e to the ipx because we're talking about this term, and the spin of the antiparticle is multiplied by e to the ipx. And you see there's a typo here, so let me fix it. So this is then minus p mu gamma mu plus m p0 e to the ipx. And so what we say then is that v of p of s is minus p mu gamma mu plus m on some v0 of s. And this is then m minus p sigma bar m v0 of s. And for p equals 0, then it's v of 0 in s is minus m is 0 plus m. And this is, well, if I factor out an m, I get m 1 minus 1 minus 1, 1 on v0 of s. And so we set v0 of s equal to s equal to, let us say, c zeta. And then this formula gives us v0 of s is m minus m c zeta, and that's m then c minus zeta minus c plus zeta, and so we can call that m beta minus beta. So the point is that for the antiparticles, we don't have the pattern alpha alpha. Instead, we have the pattern beta minus beta. And I'll choose beta plus equal to 1, 0, and beta minus equal to 0, 1. Let me just make sure this is one first choice. Very interesting. Yes. The beta equals minus beta is true. Weinberg, unlike Schwartz, gets the spinors, the anti-particle spinors right. So we could equally well choose. You might say, why would I do that? Well, because I want things to work under charge conjugation. And I was just working on that just before erasing boards this afternoon. And what I found was that if I did the naive choice, which is what you see in the book, it's you don't get the right charge conjugation. So I'll show you that a little bit later in the hour. This means that I'm going to have to do some matrix multiplication on the fly here. So what do we have? We have a different choice here of betas. And so as v of 0 plus, then what we're going to have is 0, 1, 0 minus 1, and v of 0 minus is going to be, let me get this right, 1, 0 minus 1, 0. All right, so look, I know it's a little bizarre, but whenever there's a conflict between Weinberg and everybody else, always bet on Weinberg. Okay, so what do we have then for v of p plus? Well, we'll have 1 over 2m m minus p dot sigma, or in the Lorentz sense, minus p sigma bar in the Lorentz sense of m, and then we have these two betas, and I can just rewrite that since it's the plus 0, 1, 0 minus 1. Okay, so v of p and plus then is 1 over 2m m minus e plus p dot sigma minus e minus p dot sigma. All right, I've got to use more space here. Wow, just as well that I changed that because there were more typos in this thing. Okay, so what is this going to be? It's going to be 1 over 2m m0, 0, m minus e plus p3 minus e minus p3 p1 minus I p2 p1 plus I p2. One of the very few things I memorized in life is Pauli matrices. I didn't do it on purpose, it just happened. So what do we have down here? The e's are the same, and so we have minus e minus e. What am I saying? Yeah, that's right, minus e, and then minus p3. Well, let's see, it would be the same as this, we just flip the sign of p. So it's minus e minus p3, and then this one is minus p1 plus I p2, and this one is minus p1 minus I p2 minus p3 plus p3. Okay, all that times 0, 1, 0, minus 1. Well, somebody, you guys are collectively checking, right? And 12 heads are better than 1, so you'll tell me if we make a mistake. Right? So we get 1 over 2m. So what do we get? We get p1 minus I p2 up, sign wrong because this is a minus 1. Then we get m, and we get e plus p3, and then the next one is minus p1 plus I p2. Is that right? Yeah, I guess that's right. And fortunately we have a 0, and then we have minus e plus p3 minus m. All right, that's what I got. I don't really guarantee it. But the nice formulas are, just to remind ourselves what they look like, UP plus or minus is 1 over 2m. This is, I think, the most useful formula. M, P sigma, P sigma bar, M, and then, well, alpha plus or minus, alpha plus or minus. So you just switch either 1, 0 or 0, 1. But then the V's are V of P plus or minus, or 1 over 2m, M minus P sigma, minus P sigma bar, M. And now it's, well, it's beta plus or minus beta plus or minus, but we've just learned that that beta plus is, in other words, beta plus is 0, 1, and beta minus is 1, 0. So it's opposite of what you'd expect. All right, so these then are this, if I had done the calculation, no typos correctly, we would now have the spinors. I will send them to the PDF tonight or tomorrow. What I think is nice is that this gives you the, again, if you do it correctly, obviously, you get the spinors in an explicit form, rather directly. Now, the only thing that's so far quite unexplained is why, the minus sign is explained, but why it is that beta plus is 0, 1. That's not clear. That will become clear later. Let's do now the second line of the de Blasio introduction. Namely, let's compute some property, U of P and S, U of P and S prime. And let me just quickly get a, well, I was going to say a drink of water, but I forgot to bring my water, so that's tea. So this is U dagger gamma 0. And what is this? Well, it's 1 over 4m squared, and it's alpha dagger plus or minus. I should have written S and S prime, actually. Let me do that now. S. Alpha dagger S. And then this is M, P sigma bar, P sigma M, 0, 1, 1, 0, that's gamma 0. And then M, P sigma bar, M, and then alpha of S prime. Alpha S prime. All right, now, what happened here? This is the adjoint of that, because we're taking U adjoint. So you see, if U is this, then U adjoint is alpha adjoint on, well, over 2m, say, on the adjoint of this matrix. Well, the P's are real, the sigmas are Hermitian, but when you take the transpose, you move the bar up there. So this becomes P sigma bar, P sigma M. And that's why it looks like this. All right, well, carrying out the multiplication, we just have 1 over 4m squared, alpha dagger, let me abbreviate some of these things. Then this is M, P sigma bar, P sigma M, and multiplying through we get P sigma bar M, m p sigma alpha alpha. And now, we again have alpha dagger, and what's left here is 2m p sigma bar, m squared plus p sigma bar, m squared plus p sigma bar p sigma, 2m p sigma alpha alpha. Okay, now, p sigma bar p sigma is actually quite simple because it's e plus p dot sigma, e minus p dot sigma, and you know that's your favorite combination because it simplifies to e squared minus p dot sigma squared. But any 3-vector dot sigma squared is just the square of that 3-vector. And so this is e squared minus p squared, and that's just m squared. So this expression here that looks rather complicated is just m squared. And the same thing for if you do it in reverse, p sigma times p sigma bar is also m squared. So what we have here then is that u bar ps u p s prime is 1 over 4 m squared alpha dagger 2m p sigma bar 2m squared 2m p sigma alpha alpha. And let's see, let me just skip one line. We get 1 over 2m alpha dagger. And now as a 2-vector, this is p sigma bar plus m alpha p sigma plus m alpha. Now this looks complicated until you realize that this is actually simpler. It's fairly simple. It's 1 over 2m alpha dagger 2m plus p sigma bar plus p sigma alpha. But p sigma bar plus p sigma, the complicated parts cancels and we just get e plus e. It's just 2e. So altogether, what we have here is 1 plus e over m alpha dagger alpha. And of course that alpha dagger alpha is just delta SS prime. So this is alpha dagger S alpha. And of course dagger can just as well be transposed or dot product, whatever you like. So this is 1 plus e over m delta S prime. So I've been using a normalization that's somewhat simpler than Schwarz's. And if we use Schwarz's normalization, then what we would have would be, so u Schwarz p plus minus is 1 over square root of 2 e plus m p sigma bar m alpha plus minus. So that's the way that goes. Now, it says 709.
609.
That's wrong, right? So it's 600. These politicians, if they just leave us on standard time, we'd be so much better off. In fact, I may have told you, did I tell you the story about Russia?
Something.
You
One
told
of
us
the-
many stories about Russia.
Oh, yeah.
One of of the smartest people in this department is Igor Gorlov. And his father was somewhere in the Soviet bureaucracy, I think in Moscow, when Stalin was ruling Russia. And somebody told Stalin about daylight saving time. Stalin thought it was a good idea, switched Russia, which has 11, at that time it was the Union of Soviet Socialist Republics, USSR, had 11 time zones. So we switched them all to daylight saving time. 6 months passed, and people were so frightened of Stalin that nobody thought to tell him that he ought to switch back to standard time after switching to daylight saving time. So my understanding is that the Soviet Union stayed on daylight saving time for 30 years. Now, I'm not Russian, so I've never been to Russia. I once asked to go to Russia, and they said, "Yet," unless I paid for a guide. Paying for a guide, I think it was $100 a day, so I said, "Yeah." So, all right. I'm. Let's see. All right, let's look at another part of this calculation. So we've seen that U bar U, this is U bar U in my notation. U bar U in Schwartz's notation is, does somebody have a book open to the Schwartz page? Something, but
Give me a minute.
yeah, all right. Okay, let's continue. All right, let's now switch to Schwartz's notation and do U appear as which is it? 2e. Yeah, all right. So he has 2e. So one advantage of his notation is that this is a little simpler. Now notice we're summing over spin here. Notice also that it's U is on the left, U bar on the right. So this is actually a matrix. And one of the things they don't teach in most, people don't teach in most linear algebra courses is, I mean, of course, you always know if you have a vector, you take V transpose U, and that's a standard vector. But they don't tell you normally what U V transpose is. Although, of course, I do in my book. Suppose it's 2 by 2 matrix, so then it's U1, U2, V1, V2, and this then is a 2 by 2 matrix, U1, V1, U1, V2, U2, V1, U2, V2. It's unfortunate that we often use U and V that look almost the same, I and J that look almost the same, and it's just asking for trouble, and I'm sorry about that. Okay, so what is this? This will be, first of all, with the Schwartz normalization, this is 2e plus m. So the difference is you take my normalization, divide by square root of 2, well, there's the Schwartz. So you get that thing squared. So then what do we have? We have the u, well, that's this. So that's m, p sigma bar m. And now we have a sum over s of alpha and s, that's the 2 vector. And then we have alpha dagger of S, alpha dagger of S. That's a 2-vector. So this is really a 4-vector. This is really a 4-vector. But this is a very simple 4-vector because it's just 1, 0, 1, 0, 0, 1, 0, 1. And then the rest of it is the adjoint of this times a gamma 0 finally. Because U bar is U adjoint gamma 0. And so that is U of 0 as dagger, and then the square root, and then the dagger of this. So it's M P dot sigma bar, P sig, not a dot, it's Lorentz. It looks like that. And then gamma 0 because of the gamma 0. So what this looks like then is M P sigma bar, P sigma M, gamma 0. So that's the whole thing. Now the part that I want to show you carefully is what this is. And to understand this, you just have to understand what the outer product of two vectors is. Well, what is this? Well, it is 1, 0, 1, 0. That's one of the alpha S's times its adjoint, which is 1, 0, 1, 0, plus 0, 1, 0, 1 times 0, 1, 0, 1. And now the rule for making these outer products is that you just take the first element of the vector and multiply it by every element of the row, second element times every element, third element times every element, fourth element times every, and that way you generate a 4x4 matrix. Okay, so let me go up to the front.
Just do matrix multiplication.
Yeah.
No, that's an inner product. Yeah.
Do you know what I'm doing?
Well, we can just flip it around and it makes sense.
This or
I didn't quite understand.
We answered this question. It's a tensor product. Just take it.
But the point is that these outer products are very nice, and
for outer product.
let me just stress something here. Here it's like what? It's 2014 going on 2015, and in our linear algebra classes, I don't think they teach this.
That's why you just teach people quantum mechanics.
Huh?
That's why you just teach people quantum mechanics.
Right, you need this in quantum mechanics. And in fact, in ordinary linear algebra, there's no notation for this. But back in, I don't know, 1925 or so, Dirac invented a notation for this, for outer products. And of course, it's just the bra. And so that made, that provided a notation for linear algebra that people earlier, before that, did not have. It's just one of the many remarkable contributions of Dirac. Okay. All right, so what do we have then? Let's look at this. 1, 0, 1, 0, 1, 0, 1, 0, plus 0, 1, 0, 1, 0, 1, 0, 1. And this is equal then to 1, 0, 1, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, 0. Plus 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1. If it's a little boring, that's good because then you've learned it. And now if you add this together to make a 2 by 2 matrix, what is it? It's just 1, 1, 1, 1. which is the same as 1 plus gamma 0. But I'm going to leave it like that. Okay. So what we've got then is that the sum of the spins of U of P and S, U bar of P and S, is then 1 over 2 in Schwarz's normalization, 1 over 2e plus m P sigma bar m 1 1 1 1 m P sigma bar m, and then finally gamma 0. Gamma 0 is emission. So, as are all the gamma matrices except for gamma 2, which is anti-emission. And, okay, so let's multiply this out. What I got was 1 over 2 e plus m P sigma bar m, and now this is m plus P sigma, and then this is m plus P sigma bar, m plus P sigma bar, gamma 0. So, and well, to tell you the truth, my notes run out here. Let me give you the answer from now I don't remember where the here we go. So what this should be is in other words, you multiply all that out, then multiply by gamma 0, and eventually what you get is P slash plus m, which is to say P mu gamma mu plus m. So that's a very nice expression. And if you do the V's, and notice we're summing over spins, so whether you do it right or not, you still get the right answer, namely, and it turns out to be P slash minus m, which is quite cute, isn't it? So that's the rest of it. Okay, any questions? All right, now let me talk about charge conjugation. Of course, I erased something that I'm now going to need. But anyway, let's probably erasing something else that I'm going to need. But let's just do it anyway. I think that Schwarz's treatment is unnecessarily complicated, so I think mine will be a little bit simpler. So let's start with Dirac's equation. With the electromagnetic field. Okay, so this is just I covariant derivative gamma mu minus m. And in particular, this is I d mu gamma mu minus e a mu gamma mu minus m psi of x. Now, what I'm going to do is I'm going to do that star operation, which means I'm going to complex conjugate numbers and emission conjugate operators, but I'm not going to transpose anything. And so what that gives me is minus I d mu gamma mu star minus E A mu gamma mu star minus M psi star of X equals 0. Okay? All right. Okay. Now, remember that the only Pauli matrix that's imaginary is sigma 2. Sigma 1 and sigma 3 are real. And of course, gamma 0 is real because it's just 2 by 2 identity matrices thrown together in a certain pattern. So that means that the only minus sign here, the only effect of the complex conjugation occurs on gamma 2. And it's flipped in sign. On the other hand, all 4 gamma matrices anti-commute. So here's the trick. We're going to stick in here gamma 2 squared. Now that's just minus 1, or in Weinberg's metric, plus 1. And we're going to multiply here by gamma 2. And if it was 0 before I multiply by gamma 2, it'll be 0 after I multiply by gamma 2. Okay, so we have this equation. Now, I'm going to take one of these gamma 2's and associate it with psi star. And so I'm going to have then gamma 2 minus I d mu gamma mu star. Notice the left arm is down, so you want to watch carefully. Minus E a mu gamma mu star minus M gamma 2, and then gamma 2 psi star of X. Right. So I'm going to think of this as a unit. Okay, well, when you take the gamma 2 through, if we have gamma 1, if mu is equal to 1 or 2 or 0, the star has no effect, but bringing through gamma 2 changes the sign. On the other hand, if mu is equal to 2, the star puts in a minus sign, but bringing through gamma 2 has no effect. So altogether, we get a minus sign. So this thing is then equal to I gamma mu, I d mu gamma mu, because there's always a minus sign, plus E a mu gamma mu minus M gamma 2 psi star of X equals 0. Of course, I left that one equals 0 there. Okay, so what?
Where's the conjugation?
Excuse me?
Where's the conjugation?
What?
The gamma stars.
Yeah.
The gamma star is gone because I pulled through the gamma 2. And then it hit here and made a minus 1. But, great question here. Anybody else ask a question and not get a candy? Okay. Now, remember that I said to you, the sign of M in the Dirac equation doesn't matter. Now, of course, I didn't prove that, did I? The reason why it doesn't matter is that in order to find out what M actually is, what you do is you take the Dirac equation, and let's think about the Dirac equation for simplicity without an A. You multiply by I d slash plus M, you get a Klein-Gordon equation involving M squared. And that tells you what the mass is. And consequently, the sign of M doesn't matter. Now, that may not have convinced you. Well, it doesn't matter. In other words, it doesn't. The sign of m is not physically significant. So, if you, here I tell you what, I will use red chalk then. Well, there used to be red chalk here. Well, I'll just change it to a plus. Or if you want, plus or minus, there you go. Doesn't matter the sign, but the sign of E is changed. So that means that the field, gamma 2 psi star, is a field that describes a spin 1/2 particle of the same mass but opposite charge. And so that's what we call charge conjugation. Now let's see explicitly what's going on by going over here. So just to do, so what happens to the spins, etc. All right. So you remember at the very beginning I wrote down the standard expression for a spin 1/2 particle, a spin 1/2 field, namely that psi of x is going to be a sum s equals minus the plus integral dqp to pi cubed up u of p and s, a of p and s, e to the minus I px, plus v of p and s, b dagger of p and s, e to the I px. Okay? Now, let's just see one way. Okay, let's multiply this. Let's take the complex conjugate and multiply by gamma 2. So this is a sum on S. Now we have u star of p and s, a dagger of p and s, e to the I px, plus v star of p and s, b of p and s, e to the I px, e to the minus I px. All right, so what has happened? This is a field then, well, it has a gamma 2 here, sorry. And in fact, it probably would be, normally one uses I gamma 2 or minus I gamma 2 or something. Let me just put the gamma 2 here and the gamma 2 here. Okay, well, this field annihilates particles, creates antiparticles. This field, on the other hand, annihilates antiparticles, creates particles. And now what about these spins? Well, what happens, you see, and let me do it for just momentum 0, so I don't have to write thousands of p's. So what we've got is gamma 2 on, let us say, 1, 0, 1, 0. Now the star here doesn't matter. Well, it does matter for non-zero p, but for p equals 0, it doesn't matter. So what happens here? This, of course, is 0, 0 minus I, 0, and then down here, it's 0, I, minus I, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0. Okay? just erase the thing I wanted to keep. Remember, we defined them opposite the way Schwartz did. Okay, so this is, in other words, this is gamma 2, U2, and I can star it 0, 0 plus. All right, so what do we get multiplying through? We get 0 for the first line. We get I. We get 0, and we get minus I. All right. Now, let's remember what our B's were. Now, the overall factor of I, I'm not interested in, because, I mean, as I said, you really want to define this with an I, and I'm not paying attention to that. Okay, what V is that? Well, that is V plus. V plus because we chose to have beta plus 0, 1. And then this guy has to be minus beta plus. All right? And so you see, that's why Weinberg did it that way, and Schwartz should have read the book more carefully. I better not visit Cambridge in the near future. Maybe I'll log on to Amazon, give the book 5 stars anyway. Okay, so that's the thing I wanted to explain to you as how this happens. Let's see what happens. So in other words, what this turns out to be is gamma 2 psi star of x then is sum on S apart from, well, what is it? It's apart from an I. All right, so minus I, if I multiply by minus I, the I goes away. What we have is integral dqp 2 pi q, and now we see, well, let's see. That was for plus. What about minus? So if we do it for minus, then it would, so we've seen that it works for plus. Let's do it for minus. All right. And now what we'll get, is 0. No, not 0. We get minus I. And the next one is 0. And the one after that is I, and then 0. And what is that? Well, that one, remember it would be, let's just do this. Beta plus is 0, 1. Beta minus is 1, 0. So this thing is minus I, beta plus minus beta plus. Minus. Yeah, that was the whole point. And, right. Okay. All right, so in other words, this guy is V minus. And if we multiply by, what did I say, an extra I? Minus I. Well, maybe an overall minus sign, but that doesn't really matter. In any event, what we get then is U of P and S, B of P and S, e to the minus I px, plus V of P and S, A of P and S, e to the I px. In other words, what we've got, apart perhaps from an I, for an I, is that gamma 2 psi star is the U spinors times the annihilation operator for the antiparticle plus the V spinors creation operator for the particles. And so what charge conjugation then does is just interchange particles and antiparticles, and it leaves the spin alone. All right, so I think that that's okay. Now, we only have a few minutes left. Let me go back there and do a slightly different topic. This is spinning statistics, and so I'm just going to show you part of this, and so one way of thinking about it is suppose we just have simply a particle spin up and another at x, and a particle at minus x and spin up, say. And now, if we do a rotation of pi, that's a rotation of pi. And what that will do then is it will act on each of these, and that will give us, this is 1 or minus 1. It's 1 in both cases. So this is, first of all, well, what I'm thinking of is the whole rotation. So the whole rotation rotates x into minus x, and minus x into x, so the orbital part is that, but then e to the I pi over 2 gives us an I, and it gives us 2 i's, so that's minus 1. And on the other hand, it's essentially physically the same state. Well, I don't know. Let me think of it instead in terms of fields. Suppose we have the field here. And now we do a unitary transformation. And we're taking some matrix element of that. So here, this thing is the same as so this is these are just two states, A and B, and what we have to say about those states I'll say something about them in a minute, but let's just, the simplest would be to take both of them to be the vacuum. And so this is equal to that because I'm just inserting u dagger u. And what this then is a u inverse, and now we can write this as u psi plus of x, u inverse, u psi plus of x, u inverse, and then u on b. Now leave this alone, leave that alone. This is the way, we know how fields transform under unitary Lorentz transformation. In this case, it's just a rotation. And so what happens is, this is a u inverse. This will be psi plus of minus x, but it will get the factor due to the spin 1/2 representation of the rotation group. So this is E, well, this is in fact just an I. And from here, that'll be again an I, and we'll have psi plus of minus x, and then we have UV. Okay. So this is equal to minus A U inverse psi plus of minus x, psi plus, no,
You dropped it minus.
yeah, thank you. So that's minus x, this is plus x. All right. So let's suppose this is a state that's invariant under rotations by 180 degrees. So then what we can say is that AB, the U is, yeah, let's say that, so this is in other words, minus A psi plus of minus x, psi plus of x, B, if the states are rotationally invariant. And then that tells us that the matrix element of the anti-commutator is psi plus of x is psi plus of minus x is 0. Okay? So what we have are anti-commutation relations. On the other hand, if this was a scalar field, there wouldn't have been any I. We would have had commutation relations. And in fact, if this were a particle of spin s, then what we would have gotten here would be e to the I pi over e to the I pi s squared. We get 1 for each of them. Pi is the rotation, s is the spin. So when s is a half, you get just I squared. In general, you get this. And if s is an integer, then this is e to the I pi integer, that's minus 1. Minus 1 squared is 1, commutator. If s is half an odd integer, like 3 halves or something, then you wind up getting minus 1. You have to have anti-commutation relations. Okay, so that's the way I look at this. I think we're out of time, so we might as well stop. If there are no questions, but if there are questions, I can give out candy and hang around. All right. I will try to put more descriptions. Catherine, I will try to do more. I'll try to write more words. All right.